Welcome to ICT Applications. Today we are going to discuss about the Central Processing Unit or the CPU, which is a main component of a computer system. After this session, you should be able to identify the main components of the CPU, to explain the uses of those components, and to describe the functions of the CPU. With that, let's have a look at the structure and the functions of the CPU. You know, the computer system has the CPU, primary storage or the random access memory, and the input-output devices as the main components. Out of these components, we call the CPU as the brain of the computer. This is because all the data processing inside the computer is carried out by the CPU. When a user enters data and instructions on how to process the data, the CPU fetches both the instructions and the data. Then it stores until the data processing is completed. Then it starts to process the instructions one by one. Again, the intermediate results of data processing are stored in the CPU. Once the data processing is completed, the output is sent to the output devices. Like a human can't live without the brain, the computer can't function without the CPU. Another important thing that we need to remember is the CPU decides the power and the speed of a computer. We discussed that the data and instructions have to be transferred from the input devices to the CPU, to the memory, and to the output devices. For the effective data transmission between the peripherals to take place, we have to make sure that the processor or the CPU we are using is compatible with the chipset of the motherboard. So when you are buying a processor or a CPU, make sure that it is compatible with the chipset of the motherboard. Central processor, microprocessor, chip, processor, all these are synonyms for the CPU. Then let's have a look at where the CPU is located. On the motherboard, there's a square-shaped socket. We have to place the CPU carefully to this socket. Then let's have a look at the evolution of the CPU. The first generation of CPUs were the vacuum tubes. These computers that had vacuum tubes were very large in size and had very limited processing speed and processing power. Then came the transistors. The size of the computer became smaller with the invent of transistors, and the processing speed and power increased. Then it was the era of integrated circuits. In an integrated circuit, millions and billions of electronic components are assembled together. So we can see the processing speed and power increased drastically with the invent of the ICs. Now we are in the generation of microprocessors. A microprocessor is a special kind of integrated circuit. So the processing speed and power of the modern CPUs are much higher than the early computers. Earliest computers such as ENIAC were called fixed program computers. This is because the functions are physically built to the computer. When we need to do some other task, we have to change the wiring of the computer. Here, the instructions, processing instructions were physically given to the computer using the wiring, not like giving instructions using software programs. The term CPU is generally used to indicate processes that are designed using the stored program concept. Let's see what is the stored program concept in the upcoming slides. With that, let's move forward. We already discussed that the CPU is the brain of the computer. Within the CPU, there are many microscopic circuitry, and these circuits are responsible for the information processing inside the CPU. Within a CPU, there are many units available for this information processing. A standard CPU contains processing units to interpret and implement software instructions, to perform calculations such as addition and subtraction, then to perform comparisons such as less than, equals to, greater than, then to make logical decisions such as AND operation, OR operation, and to store the intermediate results of data processing, to keep track of the current step in the execution of the program, and units to allow the communication between the other components of the computer. Now let's have a look at the CPU architecture. There are different CPU architectures. Those are von Neumann architecture, instruction set architecture, Harvard architecture, microarchitecture, and system design. Most modern CPUs are designed using the von Neumann architecture as the basis. Saying that, it doesn't mean that other architectures are not in use. When developing embedded systems, we use microcontrollers such as Atmel AVR. These are designed using the Harvard architecture. Here, in this session, our focus is on the von Neumann architecture. So, let's look at the von Neumann architecture. Von Neumann architecture operates based on the stored program concept. That means both the processing instructions and the data on which those instructions operate are stored in the memory together. The instructions are executed sequentially one by one unless it is stated that to execute them parallelly. There are 4 subcomponents in von Neumann architecture. Those are the control unit, arithmetic logic unit, the memory, and the input-output. You can see how these components are arranged in the diagram given here. Let's look at each of the components in von Neumann architecture. First one is the control unit. As the name suggests, it controls all the operations of the computer. In other words, it coordinates and manages the operations of all parts of the computer. It fetches instructions from the memory, interprets them, and directs the operations, or in other words, tells the other components what to do as per the given instructions, and during this process it has to transfer data between the input-output devices and the other peripherals of the computer. So we can say the control unit acts as an intermediary that decodes the instructions sent to the processor by the user with the input devices and tells the other units of the CPU, such as the arithmetic logic unit, what to do according to the given instructions by sending control signals. After the data processing, it sends back the processed data back to memory for storage. One important thing that we need to remember is that the control unit does not carry out any actual data processing operations or storage of data. It just sends control signals to the other components of the computer system to carry out the respective tasks. In summary, we can say the control unit provides functions such as fetching, decoding, and executing instructions, issuing control signals to control hardware, and it moves or transfers data around the computer system. Now let's discuss about the arithmetic logic unit or the ALU. In the ALU, there are two sections, namely the arithmetic section and the logic section. In the arithmetic section, the arithmetic operations like addition, subtraction, multiplication, and division are performed. Complex operations can be performed by using the basic operations repetitively. Then the logic section will perform logic operations like comparing, selecting, matching, and merging of data. The inputs to the ALU are the data words to be operated on. We call them operands, status information from previous operations. Usually this is a carry forward value from the previous operation and the code word from the control unit indicating which operation to perform. For an example, think we need to add the two numbers 4 and 5 using the computer. In this scenario, the operands are 4 and 5. These are the two numbers that we need the operation to be performed on. Here we don't have any status information, and then the control unit gives a code indicating that we need to perform addition on these two numbers. Then the output from the ALU is the result from this operation, which is 9. Depending on the instructions being executed, the operands may come from internal CPU registers or from external memory, or they can be constants generated by the ALU itself. In summary, we can say the ALU has two main functions. One is it performs arithmetic and logical operations. Then it acts as a gateway between the primary memory and the secondary storage. Then let's look at the memory component of the CPU. Registers are one type of memory available in the CPU. These registers are used by the processor to store small amount of data that are needed during the data processing. Some such instances are to store the address of the next instruction that needs to be executed, to store the current instruction being decoded, to store the results of calculations. Now let's look into some of the registers available in the CPU. First one is the program counter. Program counter is used to keep track of the execution of the program. Then the memory data register is used to handle the data transfer between the main memory and the processor. It contains the data to be written into or that has been read from the addressed location in the main memory. Current instruction register holds the value of the current instruction that is being executed. The accumulator register is used to store the intermediate results of the data processing that happens inside the arithmetic logic unit. Now let's look at some of the CPU registers. The program counter is used to keep track of the current execution of the program. It holds the address of the next instruction to be fetched from the CPU. The memory address register is used to hold the address of the current instruction that is to be fetched from memory. The other memory component available in the CPU is the cache. Cache is a very fast random access memory built within the processor. It is used to temporarily hold data and instructions that the processor is likely to reuse. The objective of having cache is to reduce the cost of fetching data and instructions from the relatively slow main memory. The CPU automatically checks the cache for instructions and data before requesting those from the RAM. It saves the time used for fetching the instructions and data repeatedly from the RAM, which is the relatively slow process, and it might keep the CPU waiting. Transfers to and from cache takes less time than transferring data to and from the RAM. So this allows faster processing of data. Then let's have a look at the buses. We can think of buses as communication channels that is used to transfer data and control signals between the peripherals in the computer. A bus is a high-speed internal connection. As we discussed, buses are used to send control signals and data between the processor and other components. There are three types of buses. First one is the address bus. It is used to carry memory addresses from the processor to the other components such as primary memory and input-output devices. Then the data bus is used to carry the actual data between the processor and other components. Then the control bus is used to carry control signals from the processor to other components. This control bus also carries the clock pulses. The clock sends out a regular electrical pulse which is used to synchronizes all the components. The frequency of the pulse is known as the clock speed, and the clock speed is measured in Hertz. Clock speed is used to measure the number of cycles that the CPU executes per second. So, higher the frequency, the more instructions can be performed in any given time. In modern CPUs, the speed is measured in gigahertz. The fundamental operation of most CPUs is to execute a sequence of stored instructions called a program. Program is represented by a series of numbers that are kept in computer memory. This diagram shows how this program execution happens in the CPU. Now let's see how a CPU designed according to the von Neumann architecture processes instructions. We know a computer program is made up of sets of instructions. Then these instructions needs to be processed within the CPU. There are 4 steps in almost all the von Neumann CPUs in this instruction processing operation. Those 4 steps are the fetch, decode, execute, and write back. The first stage of data processing is fetch. What happens in the fetch stage is the retrieving of an instruction from program memory. The location in program memory is determined by the program counter. It holds the address of the next instruction to be executed. Then the contents of the program counter, which holds the address of the next instruction to be executed, is placed into the memory address register. Then the address is sent from the memory address register to the main memory. Then the instructions at that address is found and copied to the memory data register. At the same time, the program counter is incremented in terms of memory units. Instructions to be fetched need to be retrieved from a relatively slow memory. So, the CPU has to wait until the instructions are retrieved from the memory. The next stage of the instruction cycle is the decode. What happens here is that the instruction fetched during the previous stage is used to determine what needs to be done by the CPU. At this stage, the instruction is broken down into parts that have a significance to other portions of the CPU. How the numerical instruction value is interpreted is defined by the CPU's instruction set architecture. Usually, one group of numbers in the instruction is called the opcode and it is used to indicate the operation that has to be carried out. The remaining parts are used to represent the operands that are required for the operation to take place. These operands can be a constant value or a register or a memory address that indicates a place to look for a particular value. In older designs, the portions of the CPU responsible for instruction decoding were unchangeable hardware devices. However, in more abstract and complicated CPUs and instruction set architectures, a microprogram can be used to assist in translating instructions into various configuration signals for the CPU. This microprogram is sometimes rewritable so that it can be modified to change the way the CPU decodes instructions even after manufacture. The next stage is the execute. What happens here is various components or various units of the CPU are connected to perform the desired operation. For an example, think we need to add two numbers. So, we have to perform the addition operation. Here, the ALU will be connected to a set of inputs and to a set of outputs. These inputs provide the numbers to be added and the output will contain the final sum. The addition operation produces a result too large for the CPU to handle. An arithmetic overflow flag in a flags register may also be set. The final stage of instruction cycle is the write back. Here what happens is the results of the execute step will be written to some form of memory. Usually the results are stored in some internal CPU register for quick access by the subsequent instructions. In other cases, the results may be written to the slower but cheaper and larger main memory. In loops, conditional program executions and functions in programs, the program counter is manipulated to produce the result data directly. These are called jumps. Let's see what happens in a jump. When a program is executing, its instructions are located in main memory. Then the program counter holds the address of the next instruction to be executed. When a program, let's see what happens in jumps in simple terms. We know the program counter holds the address of the next instruction to be executed. For an example, think we are executing a conditional statement that is true. At this stage, what happens is the program counter fetches the address of the instruction that needs to be executed when the particular condition is true. Here, it does not fetch the address of the next instruction, but it fetches the address of the instruction that has to be executed if this particular condition is true. Here, the jump instruction transfers the program sequence or program execution to the memory address given in the operand. Many instructions will also change the state of digits in flags register. These flags can be used to influence how a program behaves, since they often indicate the outcome of various operations. Many instructions will also change the state of digits in a flags register. These flags can be used to influence how a program behaves because they often indicate the outcome of various operations. Many instructions will also change the state of digits in a flags register. The flags register is a special purpose register, and depending upon the value of results after any arithmetic and logical operation, the flag bit becomes 1 or 0. These flags can be used to influence how a program behaves, since they often indicate the outcome of various operations. For example, think one type of compare instruction considers two values and sets a number in the flags register according to which one is greater. Then we can use this flag or jump instruction to determine the program flow. Then let's look at what are the factors that affect the CPU performance. First one is the clock speed. We discussed higher the clock speed, the performance is better. The second factor is the cache size. We discussed that the cache is a small amount of very fast random access memory built within the CPU, and the CPU looks for the particular data and instruction in the cache before fetching the data from the RAM. So, higher the cache size means higher the number of instructions and data that can be there in the cache. This reduces the cost of fetching data from the main memory. So, higher the cache size means higher the performance of the CPU. The third one is the number of cores. A core is a processing unit within the CPU. Each core can carry out fetching, decoding, and executing its own instructions. So, when the number of cores are higher, the performance of the CPU is also increased. Then there's a small activity for you to try. There you have to evaluate the available processors and their compatibility with the available motherboard chipsets. Then you have to make a conclusion. In summary, here we discussed about the central processing unit of a computer system. We call the central processing unit or the CPU as the brain of the computer. It is the component in a digital computer that interprets instructions and processes data contained in computer programs. The fundamental operation of most CPUs is to execute a sequence of stored instructions called a program. There are 4 steps in almost all the von Neumann architecture-based CPUs in their operation cycle. Those are called fetch, decode, execute, and write back. With that, we are moving towards the end of today's session. Thank you.